consider a particle of mass m attached to two identical springs of each of length L and spring constant K. The equilibrium configuration is one of the where springs are unstretched. There are no external forces on the system. If the particle is given a displacement along the x-axis, which of the following equation describes the motion for small oscillations? So therefore, what they're saying is, this is the particle of mass m, right? So this is the black dot is the particle. If it is displaced from, let's say, from this point to this point, okay, so by some small amount x. So now what is the equation of motion? Okay, so what is the equation of motion that this particle will execute? So we have to write the Lagrangian and solve the Euler-Lagrange equations. So to write, in order to write the Lagrangian, L is nothing but T minus V. Now T is nothing but half m x dot square, right? So x dot, so this is the kinetic energy term. So the potential energy term, now we have to write the potential energy term. Before that, we have to write the displacement from the equilibrium position for the particles, the single particle. So this string is stretching from, now you can see that this string is stretching from this position to this position, and its displacement is along x, and this spring is being stretched from this position to this position, and its displacement is along x. So I'll write delta x1. Delta x1 is nothing but, so this is along the first spring. Okay, so let's call this A and C, and let's call this B and C. So so this is spring AC. So this is for the spring 1. Okay, so let me call this simply spring. Okay, let's call it spring AC. So this is nothing but L square plus x square minus L. So this is from the Pythagoras theorem. So nothing more than the Pythagoras. So, and for spring BC, we have delta x2. This is nothing but L square plus x square minus L again. Same, because the identical configuration. So two springs. So now we can write the potential. So the potential is the Hooke's law potential, half k x square. Now, however, x square is nothing but delta x1 square plus delta x2 square. So now we can write the Lagrangian and solve the Euler-Lagrange equations. So the Lagrangian for the system, when you substitute this T and B, is nothing but half m x dot square minus k 2L square plus x square minus 2 square root of L square plus x square multiplied by L. This is the Lagrangian, and this is the Euler-Lagrange equations that you have to solve for the equations of motion. So when you solve this Euler-Lagrange equation, the equation of motion that you obtained is mx double dot minus k2x 1 minus 1 plus x square by L square to the power of minus half is equal to 0. Now notice that the length of the spring is very much greater than, so the length of the spring is generally very much greater than the displacement. So therefore we can use the binomial series expansion, where we say that 1 minus x to the power of minus half to first order term is nothing but 1 minus x by 2. So this is to first order terms. So higher order terms are not relevant because of this approximation. Now we have So now using this approximation, the equation of motion now becomes mx double dot minus plus, so mx double dot plus x kx cubed by L square is equal to 0. So this is your equation of motion. So this is given by option number A.